Hello everyone, welcome to our lecture series of Structure 2. So in this video, we are going to talk about method of constant deformation. We have already talked about the basics related to method of consistent deformation. So right now we are talking about the method of consistent deformation. So in this video we are going to solve our problem 1 or our example 1 for method of constant deformation. I have also uploaded my videos in Udemy, which you can find in the link in the comment below. In that through that link you can join my Udemy course for structural analysis. So firstly, let's talk about our example 1. So in our previous video we talked about method of constant deformation. So if you don't know the basics regarding method of constant deformation, you can check out that video. In this video we are going to solve this indeterminate beam by means of constant deformation. So what we're going to do is just move on to the question. Determine the reaction. We will determine the reaction and draw the shear and bending moment diagram for the beam using method of constant deformation. So in our exam we're going to ask in this manner only, and we have been given soft case as well. So usually the soft cases are not given in the exam. We can either take a reaction or moment as a redundant, but we are going to be specific in this case. So firstly, in our case A, we are going to take the reaction at a ruler A as redundant. So let me change the color. No. So what we're going to do is we're going to take the so as you can see, let me just draw this beam over here. So this is our beam. We have a uniformly distributed load UDL of 24 kN meter acting along the span from A to B over a length of 10 meter over a length of 10 meters, also called as propped cantilever beam. So as you can see, we'll have AX, one support reaction, AY and the support reaction, and moment about A, which is denoted as MA3, as and we have a roller support over here, so we'll have another as well, which is known as by. So in order to determine our static indeterminacy, in order to find our degree of static indeterminacy, as I've explained before, we can simply get by using the formula r minus 3. So we have four support reactions, 4 minus 3 equals to 1. So we have one redundant support reaction for which we can which is for that in order to solve this, so we can take one extra force. We're going to take support reaction at a roller A as redundant. So how we're going to solve this is, well, firstly we're going to remove that redundant force and we're going to draw our beam in this manner. So it's this, so this was our original beam. So now we're going to take the reaction at roller A as redundant. So we need to, what we need to do is we need to simply remove that, remove the roller support at A. So we have our UDL acting over here, 24 kilonewton per meter, and here is we have A, we have B. So once we remove the support reaction, what will happen is we'll have a deflection of this way. We'll have this deflection, and the deflection at B is noted as del B naught. This is our primary beam subjected to external load. So this is our primary beam in which the external load is not removed. So this is our primary beam subjected to, so we need to understand this properly, subjected to external load. So our external load refers to this 24 Newton per meter. So we'll have another as well, another case scenario where we will remove that external load and we will apply a unit load 1 kilonewton at point B. So in that case we'll have deflection in this manner, which is denoted as FBP, which is the deflection at point B due to unit load at point B. So I've already explained about this in the previous video. So if you watch the previous video and if you move on to this problem, it will be much more easier for you to visualize and have your concept clear. So this is our primary beam subjected to unit redundant by. So as we remove the support roller support at B, what we will be doing is we will apply we will apply will apply unit load of 1 kilonewton at point A. So moving on further, so we can write this as a primary beam subjected to, this is our primary being subjected to unit redundant viewer. So I have redundant over here, so you can see this over here. So now our main thing will be we need to let me use different over here. use the highlighter. What we're going to do is we're going to use our compatibility equation, which is del b, deflection at b equals to 0. So this so the deflection at b needs to be 0, which is the summation of del b naught of our case first plus fbb dot by equals to fbb dot by is our unit is our redundant by. So let me select a color from here. So what we're going to do is we're going to use our compatibility equation, which is going to be del b naught equals to 0, which is simply del b naught plus fbb dot by equals to 0. So what we're going to do is we're going to write del b, deflection at b equals to 0, which is equal to del b naught plus fbb dot by equals to 0. So del b naught comes from our first case scenario and del fbb dot by comes from our second case scenario. So simply our redundant force by will be equal to minus del b naught divided by fbb. So in order to find our by force, which will be equivalent to our roller support at b, what we are going to do is we need to determine del b naught and fbb, and we will be determining those values by using virtual work method. So we have our formula del b naught equals to m naught mb dx, m naught mb divided by ei dx, and fbb equals to mb square divided by ei dx. This is our formula. This comes from a derivation, so we don't need derivation right now. We just need to focus on the formula, which is so let me write it down over. This is a really important formula, and to remember this formula, del b naught equals to m naught mb divided by ei dx, whereas fbb equals to mb square divided by ei dx, where m naught refers to bending moment at any section due to external load. So m naught is for this case scenario, bending moment at any section, any section, let's say at x section, due to the external load of 24 kilonewton per meter in our case, while MB refers as bending moment at any section due to unit load at B. This is our case scenario 2. So let's write this as of case A and of case B of the actual beam. So M naught is refers to the bending moment at any section due to external load, while MB refers to as the uh, bending moment at any point. It refers to the bending moment at any section due to unit load at point B. So by using Boswell work method, we can find m naught and mb. So in order to find so firstly let's move on to our so let me draw our this figure. Let me copy this figure, and let me paste it over here. So this is my figure. So we need to look at this figure in order to find our firstly for del b naught, because del b naught refers to m naught mb divided by ei dx. So first what we need to do is let me draw this section over section A. We will take the section A from A to B. So let us this. So what we have over here is we have our beam in this way. We have a UDL of 24 kilonewton per meter, and we have a section A and section B over here. So we have we can take origin at any point. So this is similar to what we have done in structure 1. So let me take at x distance from point B, for firstly we need to calculate m naught. M naught is bending moment at any section due to external load. So due to external load, so we have our 24 kilonewton. So we have our origin. We can take origin at origin as B or origin as A according to your choice. Right now we are taking origin at B, and we have our limit from 0 to 10. So the limit is for x value. So this total length is 10 meters. So the value of x will vary from 0 and 0 at B, while moving till A, it will be the value of 10 meter. So the limit is 0 to 10. Firstly we are going to find m naught and then mb. So in order to find m naught, what we will do is naught, m naught will be equal to so let me just, so we have 24 kilonewton meter over here. So what will happen is we're going to so bending moment at this point, bending moment at this point taking origin at b, so we're moving from right to left. 24 kilonewton meter is acting downward, so 24 kilonewton meter is acting downward, and it is going to produce it is going to produce clockwise movement. So while moving from, we have our rule, while moving from left to right, clockwise movement is taken as positive, or while moving from right to left section, clockwise movement are taken as negative. So you need to remember this. While moving from left to right of a beam, clockwise movement are taken as positive. While moving from right to left, so let me draw it over this over here. uh, so this is my structure. So this is point A, this is point B, and I'm taking a bending moment at point X, and this is point X, and 24 kilonewton meter is acting downward. So if this was force, let me replace it by a simple force in order to explain you. This is X. So what with reference to this point, it's going to produce anti-clockwise movement. So you can imagine in this way, this is my pen. uh, a certain load is acting this way, it will it will try to turn the beam in this direction, which is clockwise direction. So clockwise direction is taken as negative. So what we'll do is, the caution, we are going to write this as, we're going to put a negative sign, minus, and 24 into, it is acting over a span of x, so I'm going to multiply it by x, and this point will act at a distance of x by 2. This is going to be minus 12 x square. So full, this is this makes sense. This is our simple structural logic, so let me explain that as well. So 24, so in order to convert this into point load, we need to multiply the UDL value with the span, which is x, 24 into x, and it will act at a distance from half the span, which is x by 2. So in order to find the bending moment, what we'll do is we'll simply multiply the load, which is 24x into x by 2. 24x into x by 2, we get the value of minus 12x squared. So our value of m naught, m naught will be minus 12 x square. Similarly for md, we're going to take this as x. We're going to take this as x, because this bending moment and it's unit load at b. So for that case scenario, what we're going to do is, let me draw this. Let me redraw the beam. So I'm explaining this step by step. This is our first video for the constant deformation. So here we go. This is our A and here is our B. So we need to find bending moment at distance x from origin B. So we have a unit load 1 kilonewton acting upward. So this will try to turn our beam in this direction, which is anti-clockwise direction. But while we're moving from right section towards the left section, right towards left. While moving from right to left, clockwise movement are taken as positive, whereas anti-clockwise movement are taken as positive. Sorry. uh, while moving from, let me write, while moving from right to left in a beam, so we're right now moving in right to left, uh, clockwise movement, this is our clockwise movement, sorry, clockwise movement are taken as negative, whereas anti-clockwise movement are taken as positive. So you need to remember this. It will be very helpful for all of our structure. So, but while moving from left to right, clockwise movement are taken as positive, whereas anti-clockwise movement are taken as negative. It becomes opposite. So right now, to remember this, draw this right now. So right now we are moving from right to left, and 1 kilonewton is going to produce anti-clockwise movement, so we need to take it as positive. So we get that value of x, just x1 into 1 unit load into distance x, we get the value of x. So hopefully this is clear till over it. So if you have any comments, you can comment down below and answer you over there. So now we have our original formula of del b naught, which is equal to m naught. We have our m naught minus 12x square into mb, which is x. So this will act from distance. We need to put on our limit as well. So our limit is from 0 to 10. So we put on the limit for our antiderivative, and we get 0 to 10. M naught is minus 12x square into mb is x divided by ei. So this becomes minus, so let me write it over here. This becomes 0 to 10 minus 12 x cubed divided by ei dx, and this becomes minus 12 comes out, so we get x4 by 4. 0 to 10, this becomes minus 12 by 4, 10 to the power 4 minus 0. So on solving this, 4 3 is double, as we get minus 3000 divided by ei. Similarly, we have FBB equals to 0 to L MB square divided by EI dx, which is our as I explained before, the formula for MBB from partial block methodology. 0 to L, which is limit MB square divided by EI dx square. So we have limit 0 to 10, MB is x square divided by EI dx. So this becomes x cubed by 3. Limit 0 to 10 is 10 cube by 3, which is 10,000 divided by 3. Yeah, okay, this is right. So from that we get our value of f del b naught and fbb. Then we have our formula. So as I explained before, we started with del b equals to 0. It's a complete del b naught plus fbb dot by equals to 0 from swap case a and b. So we got by equals to minus del b naught divided by fbb. So now we have our for a value of our del b naught and fbb. So on solving that, we get our value of by as 90 kilonewton. So what does this mean? So this means when we remove that roller support from point B, in order to remove that this roller support from point B, we need to provide an upward force of 90 kilonewton. So we had taken this by as the direction as upward, so our value of by will be 90 kilonewton. So now there are other unknowns ay, ax and me. We can simply find them. So first, in order to find the value of our ey, we take efy equals to 0. We take forces acting downward as, sorry, we take forces acting upward as a positive, so that it becomes ay plus by equals to 9, so equals to the value of udl is 24 into 10. So this is 24 kilonewton per meter acting over a span of 10 meter. So we get the 24 into 10. From this we have our ay becomes 240 minus by, which is equal to 90. This becomes 150 kilo Newton. Similarly, we get our value of MA as well. We can take uh, so the value of AX will be 0, since there are no any force acting in the original direction. Now for our value of MA, we can take a moment about B equals to 0. So we have taken moment about we can take moment about any direction, moment about A. So currently we have taken moment about A equals to 0. Moment about, so we're going to take clockwise moment as positive. Moment about A equals to 0. So we get that as 90. So where our 90, this is acting, we get this as MA. MA plus this is acting, this is 24. 24 into x is 10 into it will act at half of the span into 10 by 2 minus, this is acting anti-clockwise, so we take this as negative. 90 into 10 equals to 0. So we get our value of na as 90 into 900 minus 24 into 10 into 5. So on solving this, we get our value of na as 300 kilonewton meter. So we know the value of ma, we know the value of by, and we know the value of ay, and ax is 0. So knowing all this value, now we can easily create our shear force diagram and bending moment diagram. This is our part 1 series. In our part 2 series, we'll find out the part 2 series for the same problem. We'll find out the shear force diagram and bending moment diagram in this way. So I'll teach you in the next video. In the next video, I'll also explain about how we can solve this indeterminate beam by taking moment at A as redundant. So currently we took reaction at roller A, roller B, reaction at roller as redundant. In the next part, we'll be taking moment at fixed and moment at A. We'll take this moment as redundant while keeping this roller separate. So I'll explain how we can do that in the next video. So if you like our video, do subscribe the channel, do like the video, and do share with your friends. And you can check my Udemy mention in the comment for further more videos related to structural mechanics. Thank you.